And what I'm going to do is describe to you some technologies that we use to prototype circuits. This is something you can do at home. The boards I have here are basically, this one's about $99, I think. So these are things that ordinary, they're cheaper than a textbook, at least in the modern world. You can program them up completely on your laptop, and you can build circuits that are pretty sophisticated, right? So the device, the field programmable gate array that's in the middle here, has the equivalent of about 1 million gates of logic in it. And you get to tell what each of the gates does. So you can build substantial size circuits here. So the basic layout of the FPGA is that we have these what they call combinational logic blocks, CLBs, which are the sort of basic building block for the programmable logic. And then there's a programmable interconnect. So think of this as a big set of Manhattan streets. So there's actually many wires in each of the little gray areas. And you will spend time, or the tools will spend time, figuring out how to route signals, west, south, east, north, and connect them up. And so they'll actually figure out how to, and then at each intersection of the wires, there's a little programmable switch. So the programming that's involved is figuring out what logic function is computed by each of the little logic blocks. We do that via a truth table that we load into essentially it's a little memory that we load up with a truth table. And then the interconnect is like a little set of traffic lights that basically you set up a path, and think of it like a PC board, except that it's a programmable PC board. There's special things. There's, in this case, in this chip, there's about 300 pins around the edge. In the bigger FPGAs, you can get up to 1,200 or 1,500 pins around the edge. They have built-in memories. So this is a memory that's 32K by 1 bits all the way to 512 by 8 bits. You can figure what shape and the same total number of bits. You're just configuring how wide versus how deep it is. That's one of the things you can program. And then special things like multipliers so you don't have to actually build them out of the low-level logic gates. And this whole thing, when I power this on, there's a little memory that holds all the programming bits, and that just gets, in the first couple milliseconds, that gets loaded in to program up all the logic and interconnect in this chip, and away you go. This chip is slower than, your custom Intel processor. The beta I will show you later is running at 50 megahertz, not a gigahertz. On the other hand, you can do have a lot of fun with digital circuits, even at these, tens of megahertz clock rates. Here's what an actual FPGA chip looks like. The configurable logic blocks, the multipliers, the pins around the edge. This is a huge one, right? This one here is many millions of logic gate equivalents. And so we used a big chip here in a course 6173 where we actually built a little 16-core multiprocessor completely with programmable logic. We designed the processor, we designed the interconnect, we designed the memory interfaces, all writing Verilog. And we could actually get that processor to run, and each processor had an instruction cache and a data cache and things like that. We could actually program up this chip to be a quite sophisticated experimental platform. So if you ever want to build a digital system yourself, either for fun or profit, you might find an FPGA to be FGPA, perhaps. Dyslexia strikes. Okay. It's like that. I remember this great cartoon which had somebody standing there with a big poster that said, "Dyslexics untie," which I thought was, you can think about that. Okay, so what does a configurable logic block look like? They're built up about these interconnected slices, and I'm going to show you what a slice looks like. A slice has a lookup table. So this is a lookup table. This particular lookup table basically takes in 4 wires. So what it does is you can compute any logic function you want of 4 variables. Right? So think of this as a 16-element, or yes, as a big table. So for every possible combination of the values on the 4 wires, I can produce an output value. And what that logic function is, that's one of the things that's programmable. So one of the things I feed this chip is a lot of little truth tables. And when you write all your logic equations in Verilog, you know, the WRF is, you know, interrupt request, not interrupt request, and reset, and, you know, this signal from the control ROM. You're doing all this, you describe the logic when you want WRF to be true. That the compiler figures out how to put all that into these 4 variable truth tables. So when I say something has a lot of logic gates, I'm talking sort of like 2 input logic gates. There's not actually millions of these lookup tables. There's tens of thousands of these lookup tables. But the compiler is very good at figuring out how to combine multiple multiple Boolean operations into one lookup table. There's a flip-flop that you can route the value to. So you basically, for every logic gate, there's a register that you can use. There's a couple other little things here. We basically have a very fast carry chain. So there's extra logic built into the circuit to generate these very fast carry chains. So the adders on these FPGAs run quite quickly, much more quickly than if you built them out of logic gates, this carry chain. Remember, in your ripple carry adder, it's the carry-in, carry-out path which sets the critical thing. This is a very highly optimized. This is almost a custom circuit for doing that. So these adders can run at hundreds of megahertz. You know, a couple nanosecond. You know, for like a 32-bit adder, which is neat. And there's enough stuff in here to do multiplies and things like that. Okay, so the basic building blocks are lookup tables and flip-flops. Another building block is this fancy memory system that I told you I could configure it to be sort of any shape I wanted to be. It's actually a dual port memory. Each of these hardware blocks comes with 2 ports. It's a synchronous memory, and I won't bother to describe the details of that, but think of it as a pipeline memory system where there's always a clock edge between the specification of the operation and when it actually happens. So for instance, if I'm reading data out, I have to put in the address before the clock edge happens, and then the answer comes out a couple of nanoseconds later. So it's not a combinational path like we're used to. Ooh, here's that programmable interconnect. So each of these guys, the CLBs, those are sort of the programmable logic blocks. And then there's this very weird connection of wires, some of which just meet up here at these giant Manhattan intersections. And at these intersections, you get this little row of programmable switches. And you can see that you can basically route a signal that's going east-west. You can have it continue to go east-west, or it can make a turn. It can go, you know, south or north. And in fact, just like in regular intersections, if this signal is coming in from the west and going south, you can get another signal coming in from the east and going north, right? So it basically can make a connection between the 4 neighbors and then across horizontally and across vertically. So these are little programmable switches, single N-channel FETs that we turn on or off to make an electrical connection across. And you can say, well, I'd need a lot of those to make, you know, a 32-bit bus. And the answer is yes, you do. Happily, the chip has a lot of these things. If each one of these things is a bit, okay, you can see that there's a lot of interconnect for each, you know, possible logic gate output. And that's what's needed to basically get information across the chip reasonably. Here's a really blown up view. Here's that programmable switch matrix I told you. And here's all the detailed connections that are happening between the long wires that go between the blocks and then from a little local interconnect into each logic block. So you can see the compiler has a lot of things to figure out how to get the signals all routed around. The routing is not so good because the MOSFETs are like little resistors. So this programmable interconnect is really neat. It's programmable, but it takes a while to, you know, charge up and discharge a highly capacitive signal run through what is essentially a whole series of resistors at each of the intersections. So what does that mean in terms of timing? Well, what it means is that somewhere around 1/2 to 2/3 of your entire timing budget is devoted to simply the transmission of signals around the chip. Right, the lookup table is pretty fast, the flip-flop is very fast. What is slow on an FPGA is the routing of these signals. So that's always a little disappointing. On the other hand, it's fairly realistic. I mean, the Intel engineers probably spent as much time thinking about how to get information from here to there quickly And mostly they spend a lot of time making sure that here and there are pretty close together, so they don't have to put much of a timing budget into that part of the put much of a timing allocation into that part of the budget. But here, the tools take care of it, but when you finally look at your timing analysis and you're going, oh my God, my 5 gigahertz beta is only 50 megahertz because I'm spending huge amounts of time just watching the signal get from one gate to another through this Manhattan geometry. There's a very highly engineered clock circuitry in here. The real goal is to get the clock to arrive at all the flip-flops. So altogether, this chip probably has 30 or 40,000 flip-flops in it, and you have a rising clock edge that that says, "Oh, here's the clock." It will basically arrive at each of the flip-flops wherever it is on the chip. Okay, wherever that signal is on the chip, that flip-flop is on the chip, within 30 picoseconds of each other, right? So there's a lot of engineering that goes to make a very symmetrical. You can see there's this notion of the vertical spine, the horizontal spine. The idea is that the distance to each clock signal is carefully tuned to be about the same from the clock drivers for every flip-flop in the chip. So that turns out to take away a lot of the complexity of designing these fairly large clock systems. They've already figured out how to get the clocks to the right place at the right time.